Hi, let me welcome you to this course on feedback and control systems. I am Brian Dineros, your professor for this subject for this semester. We'll be seeing via Google Meet soon, but right now allow me to orient you about feedback and control systems in this video. I'll be describing the course and walk you through each of the modules. In the future, you'll be graduating in this program, and it is expected as an engineer that you have gained the ability to design a system, component, or process to meet desired needs within realistic constraints such as economic, environmental, social, political, ethical, health and safety, manufacturability, and sustainability in accordance with standards. On top of that, you should be able to identify, formulate, and solve engineering problems. Feedback control is an interdisciplinary field in that control is applied to systems in every conceivable area of engineering. Consequently, some schools have separate introductory course for control within the standard disciplines, and some may have a single set of courses taken by students from many disciplines. However, to restrict examples to one field is to miss much of the range and power of feedback. But to cover the whole range of applications is so overwhelming. In this course, we'll explore the interdisciplinary nature of the field and provide review material for several of the most common technologies so that students from many disciplines will be comfortable with the presentation. Just as an overview, this course deals with time and frequency response of feedback control systems. The topics covered include time response of first order and second order systems, modeling, transfer functions, pole zero map, stability analysis, root locus, Bode plots, compensators, PID controllers, and introduction to state space techniques. Well, after completing this course, you must be able to familiarize with various systems exhibiting control mechanisms and understand their operation. Develop the value of being analytic and able to apply learned concepts to improve systems. Third, understand and appreciate feedback control. Apply feedback and control system level thinking and demonstrate knowledge of concepts in dealing with feedback and control systems. Listed here is an outline for the course. Let me itemize each of the modules. First, an overview and brief history of feedback control, dynamic models, dynamic response, a first analysis of feedback, the root locus design method, the frequency response method, state space design, control system design, principles, and case study. Plus, we will be having a PLC programming exercise in this class. We'll discuss PLC later in this course. So let's talk about an overview of this course. In Module 1, the essential idea of feedback and some of the key design issues are introduced. This module also contains a brief history of control, from the ancient beginnings of process control to flight control and electronic feedback amplifiers. It is hoped that this brief history will give a context for the field, introduce some of the key figures who contributed to its development, and provide motivation to the student for the studies to come. Module 2 is a presentation of dynamic modeling, and it includes mechanical, electrical, electromechanical, fluid, and thermodynamic devices. In this module, we'll be writing the dynamic equations of various electrical and electromechanical systems. Finally, we will show how to linearize simple nonlinearities. Module 3 covers dynamic response as used in control. The Laplace transform is reviewed in this module. It is a mathematical tool that for transforming differential equations into an easier to manipulate algebraic form. Also in this module, we will deal with block diagrams and its algebra, which will be very useful in designing control systems. In addition, we'll talk more on transfer functions. Then, we'll discuss the correlation between pole locations and transient response and the effects of extra and zero and poles, which tells us a great deal about the system characteristics. When feedback is introduced, it is possible that the system may become unstable. To study this effect, we will discuss stability of dynamic system by examining the coefficient of the system's characteristic equation. Module 4 presents the basic equations and transfer functions of feedback, along with the definition of the sensitivity function. With these tools, open loop and closed loop control are compared with respect to the disturbance rejection, tracking, accuracy, and sensitivity to model errors. Classification of systems according to their ability to track reference signals or to reject polynomial disturbances is described with the concept of system type. Finally, the classical proportional, integral, and derivative or PID control structure is introduced, and the influence of the controller parameters on a system's characteristic equation is explored along with tuning methods. Following the overview of feedback in Module 4, the core of the subject presents the design methods based on root locus, frequency response, and state variable feedback in Modules 5, 6, and 7, respectively. In the last module, the three primary approaches are integrated in several case studies, and a framework for design is described that includes a touch of the real-world context of practical control design. Programmable logic controllers, or PLC, and supervisory control and data acquisition, SCADA, are also included in this course. We'll touch on their applications and perform exercises on each. Before we end this presentation, allow me to remind you that your course syllabus will be uploaded for your reference. Should you have any concerns, you may directly message me. Always read the handbook for other important information, guidelines, policies, and reminders. Thank you for listening.